Hi everybody, my name is Jeffrey. I have been working with OneClass for 3 or 4 years now. I'm currently an economics and SAT tutor. I recently graduated from Cornell University with a bachelor's degree in policy analysis and management, as well as minors in both business and applied economics. And I'm really excited to be here to be working with you guys today. I think the plan is to just cover some basic SAT math section content, kind of give an overview of what you can expect, and also cover some of the foundational principles that you might come across when you're doing your SAT math preparation or actually taking the test. With that being said, we can move straight into our content for today. So a brief overview of what I've planned for today. We've got about 2 hours. This will most likely take up basically that amount of time. I wanted to start off for those of you who really haven't done any SAT kind of prep before, any overview or background into what you can expect on the SAT, and give you kind of an idea of what the structure of the test is like and what you can expect when you open a test booklet. The second thing I'll cover after I go over those kind of structural background ideas is just linear equations, which is saying how do we apply some of the concepts we learned in math classes before, like linear equations, to the SAT type of questions. And the third thing we'll do today is also talk about word problems, because that's something that is heavily tested on the SAT as well, and specifically how do we work with the translation process of word problems into basic algebra. So we'll start with that SAT overview. So there's really and this is really helpful because Kaplan and College Board and Khan Academy have really put out a very, very transparent way of looking at the types of topics on the test. And there are 4 main ones on the math section. The first one is Heart of Algebra. And that really focuses on things that you've definitely seen before in the classroom. Things like linear equations, systems of equations, and functions. These are kind of your straightforward algebraic problems. And a lot of what we'll talk about today is really going to focus on the Heart of Algebra section of the math section. The second main category is going to be problem solving and data analytics. And that's more so interpreting things and using things like ratios, percentages, proportional reasoning, and applying that to real world situations. And those situations can also sometimes involve graphical representations or statistical data. The third main topic is what is known as Passport to Advanced Math, which is really just College Board's way of telling us that this section, there are going to be questions that involve more complex equations and functions, things like polynomials and other more advanced algebraic concepts that you will almost also definitely have seen in the class before, which will just kind of prep you for college courses in calculus or advanced statistics. And so that's going to be another portion of the test that you should expect to see as well. And finally, there's a fourth section, which is very kind of broad and vague, and that's the additional topics in math. But really what that refers to is simply just geometry, proportional reasoning, or trigonometry. And it's important to note that the additional topics in math is one of the smallest sections. And we're actually going to go into kind of a summary that College Board has provided of how many of these questions can you roughly expect to see on a test. So that's the dimensions of section content, right? Like what are the 4 types of questions or categories of questions that we can expect to see on the actual test day. The other half of that, kind of background that you need to know is what is the actual format of the test, right? So we can break that down as well. So there's going to be 2 sections within the math section of the SAT, and those are going to be your calculator and your non-calculator sections. And as they are aptly named, one of the sections you are allowed to use a calculator, a graphing calculator, and on another section you are not allowed to use a graphing calculator to answer those questions. So that's just something to be prepared for. It's important to note that even if a question allows for calculator usage, in a lot of scenarios it is actually still faster to not use a calculator and go through the conventional method of calculating the answer just for efficiency's sake, because a lot of these questions are designed to be able to be solved without calculator use. So that's just something that's important to note and something that you can incorporate into your test taking strategy. The other kind of dimension of the SAT math section is the types of questions involved, and these types, the split between multiple choice questions and gridded response questions is seen in both the calculator and a non-calculator section. I'm fairly certain you're all very familiar with multiple choice questions. We see that all the time in school and in classrooms. And 80% of the SAT math section is going to involve multiple choice questions with 5 possible answer choices. And so there's no penalty for an incorrect answer. And that means essentially in your test day strategy, you should always be aiming to fill in an answer even if you are just guessing, because you don't get penalized for guessing a wrong answer, and on the off chance you get it right, you get that point. So that's just kind of a little bit informative of how you would approach the test on test day. And then the second category of questions is going to be gridded response questions. And so these are kind of harder to understand, so I've attached an image on the right. And essentially it's saying almost like a free response where the student is asked to grid in an answer in this format. It can be a whole number, it can be a fraction as we see here, it can be a decimal, and that's just something that you should be prepared to see on the SAT test day, because it's guaranteed going to be there. Again, these are a minority of questions, roughly 20% of questions, but they will definitely be there. And therefore, these questions, there's no, like, for example, process of elimination for a grid and response question, right? Because you aren't given answer choices. So that's kind of a good section breakdown of the kind of split of the structure of the test. And finally, there are a couple of slides here that, again, are provided by College Board, which are, I think, very good to give you, again, a holistic idea of what the SAT Math section looks like. So again, we have our calculator portion, which is always 38 questions, and you're given 55 minutes to answer those 38 questions. And you have your non-calculator portion, which is 20 questions, and you're given 25 minutes to answer those 20 questions. So your total time spent on math on the SAT is going to total 80 minutes between the two sections. Again, multiple choice is 45 out of the total number of questions, which is 58, and your student-produced response is about 13 questions, right? So the rough percentage breakdown is here. Kind of a more exact breakdown that we were talking about from last slide. And then if you wanted to break this down in terms of content categories, you could see that Heart of Algebra will take up roughly 11 questions, so 30% of the test. Problem solving and data analytics is 45%. Passport to Advanced Math is 18%. And additional topics in math is 8%, for a total of the 55 minutes here. And so in these questions, what's really important to note is that problem solving and data analysis for the calculator portion of the test is the core kind of tested subject out of the 4 categories. And so it's really important that you have a firm grasp of these areas, and that's quickly followed by the Heart of Algebra section. So this is the calculator portion. And for the non-calculator portion, we also have this breakdown of about 75% multiple choice, 25% gridded response, and then we can see here that there are no problem solving or data analysis questions on the non-calculator portion. We're purely testing Heart of Algebra, Passport to Advanced Math, and additional topics in math. And so roughly even split between Heart of Algebra and Passport to Advanced Math, and a slight remainder of questions left for additional topics in math. Again, for this section, for the non-calculator, it's important to note that you're really being tested on your grasp of algebraic concepts, both basic and advanced. And so that's where the core kind of questions will focus on the non-calculator, and that's what you should be prepared to see on test day. So the reason I tell you all these things is just because I feel like even if you have experience with the SAT, and you're saying, oh, this is all kind of review, it's important, I think, to note, just get a sense of where is the focus on the test. It shouldn't just be, well, I know the math section's about math, but it should be, well, I know when I go into the calculator section, I'm going to be asked a lot about statistics and analysis. When I'm going into the non-calculator section, I'm going to be asked a lot about algebraic concepts. And so knowing what the test makers have in mind when they're designing these tests can really inform how you study, how you take the test, where you kind of focus your efforts on in the lead up to test day, if you feel like there's certain areas you want to focus on. And that allows you to really get that kind of upper hand on other people who might just be approaching the test kind of like a blank slate and saying, you know, I'll just answer whatever question gets thrown my way. Right. So then in terms of the overall contribution of questions to the types of questions being asked, you have the heart of algebra, which more specifically involves these concepts. And the reason I'm pointing out these specific categories is because, again, you know, this isn't something that I came up with. This is something that College Board came up with. So these are the concepts and subscores that they are testing when they design the questions that you'll be answering. So you'll be asked about linear equations and systems of equations, which is something we'll talk about today. You'll be asked about inequalities. You'll be asked about the relationship between these equations and graphs. So all of this stuff is stuff we'll touch upon today. Problem-solving data analysis, we're talking about, again, ratios and units, representing and analyzing data and probabilities. In Passport to Advanced Math, we're talking about, you know, creating algebraic expressions, talking about quadratic and nonlinear equations, and exponential and nonlinear functions. And so these are, again, some of the more advanced concepts that will prepare you for eventually calculus in college. And finally, your additional topics in math really refers to areas and volume, geometry, trigonometry, and some of those kind of more basic questions. Hopefully it gives you a good idea of what the test overall will look like. And again, all these resources are also online if you want to take a look at those as well. Great. So now that we have a good foundational understanding of, you know, what am I getting myself into when I take the SAT math section, we can move on to talking about some of the core concepts. So today, because we are limited in time, we're really focusing on heart of algebra. And I think when I look at the concepts tested for heart of algebra, it really comes down to different questions about linear equations. So basically the structure of how I've designed the presentation for today is really saying, okay, linear equations is such a broad category of topics. It can be tested in so many different contexts, so many different types of questions. What are the different ways in which I might see linear equations appearing on the SAT math section? And hopefully after you watch the stream today, you'll get a good idea of all the different ways you can flip open the SAT math section and see a question, be like, that's a linear equation question, and I know exactly, or I can expect that I've already done a question like this before. And so we can always just start with the basics. The first type of linear equation you might see is simply having a linear equation show up on the test written out for you and say, what is the solution to this equation? I think that's a very straightforward kind of question, very little interpretation involved there. And this is really just testing how comfortable are you with solving algebra and solving a linear equation. So we can tackle this together, taking a look at the equation given to us. So the question says, 3 times 1/2 minus y equals 3/5 plus 15y. What is the solution to the given equation? So the first thing I would do is just write out the equation for myself and then kind of go through the motions, right? So we're doing multiplying 3 into the parentheses, we get 3.5 minus 3y equals 3/5 plus 15y. The next step, we can try and get all of the variables on one side. So add 3y to each side, we get 3/2 equals 3/5 plus 18y. And then we want to get all the constants on the other side together. So we get 3/2 minus 3/5 on both sides. That equals 18y. And finally, we're left with this kind of basic equation. So one way you could do this is just kind of subtract through and do multiplication. But to make it easier, it actually would be a shortcut if you just multiply both sides by 10 to make it an easier division. So if we multiply both sides by 10, we get 30 over 2 minus 30 over 5 equals 180 times y. And solving for that, we get 9 equals 180y. and the solution to the equation would therefore be 9 divided by 180, or 1 over 20. So hopefully we see that this is, again, just a test of fundamental grasps of linear equations and how to solve them. The step that you multiply 10 on both sides, again, you don't have to do that. There are a lot of different ways that you could approach this question, but as long as you're getting the right answer, whatever makes it the easiest, the most efficient, the quickest for you to get the right answer, that should be the approach you take. Okay, so we'll take a look at another question, which again will be on face value the exact same. It's just a test of how comfortable are you solving a linear equation. So in this scenario, we'll read the question. It says -2 times 3x minus 2.4 equals -3 times 3x minus 2.4. What is the solution to this equation, right? So we can evaluate this question for a second and say, okay, well, we could do the same thing we did for the last question, and we could just multiply through, to solve for, get all the variables on one side, the constants on the other, solve for the variable. But we can also, well, first I would write down the equation for myself, but then we can also say, well, wait a minute, this is not just, a random linear equation. There's something unique about it, and that's that both terms in the parentheses are the same, right? 3x minus 2.4 is on both sides of the equation. And so we can ask ourselves, well, if -2 times this term is equivalent to -3 times the exact same term, what does that tell us about what the term must equal, right? Because we know that in most cases that's not going to be possible. And so what we can notice from the structure of this equation is that 3x minus 2.4 has to equal 0 in order for this equation to be satisfied, right? Otherwise, there's no other number that 3x minus 2.4 could be equal to that would allow us to multiply it by -2 and by -3 and have them still be equivalent. So it has to be equal to 0. And that kind of saves us the trouble of distributing the constants and so forth. And we can just kind of set up that final equation of 3x minus 2.4 equals 0, right? And so that is a very simple linear equation. We want to have constants on one side and variables on the other side. So we add 2.4 to both sides. We get 3x equals 2.4, and then we can divide both sides by 3, and we get x equals 0.8. Hopefully that makes sense. Again, is it required that we solve it this way? No. We could, again, multiply -2 out throughout the expression, multiply -3 out throughout the expression, and we would see eventually that we would get to the same answer. The question is, however, which one is going to be more efficient? Which one is faster? And so again, because again, the SAT math is a timed test, if we do this shortcut, I'm going to call it a shortcut, and we set 3x minus 2.4 equal to 0, that's going to save us some time that we can dedicate towards other questions. So remember, it's not just, first of all, yes, it is about getting to the right answer, but also if you can get to the right answer quicker and faster and more efficiently, then that will make it easier for you to do well on the section. Okay, so I hope this kind of explanation or breakdown of the approach we took for this question kind of makes sense. So again, so these are just, very straightforward. The SAT provides you a linear equation and you solve it, right? So what are some other ways in which we can see linear equations being tested? And so the next, I think, evolution in linear equations is just add another one, and that makes it a system of equation, right? And so systems of equations, and this is hopefully something that you're familiar with in math class, it can be solved in 3 unique and different ways, right? And you can use any of these ways interchangeably. They all give you the right answer. So the first way is simply graphing. And we'll go in a few slides later about exactly what are the scenarios you can expect when you're graphing, but if you just graph a system of equations, you can quickly see where the solutions are or whether there are any solutions at the intersection points. The second way you can solve a system of equation is substitution. And so that's where you have the 2 equations, and basically you find one variable in terms of the other variable. So in this case, y is equal to -3x plus 15, and we would solve this by substituting this -3x plus 15 in for y in the second equation, right? So that will give us variables of all x's in this equation, right, and all constants remaining, and we would be able to solve for x, and then with x solved, we could solve for y. So that's substitution, and that is, again, a very common way that you would be solving these these systems of equations. And then the third way is elimination, and so that's basically saying if you can subtract one of these equations from the other equation and eliminate one of the variables, then you would again be left with only one variable in the equation, allowing you to solve for the question. So in this case, we could say, well, let's multiply the bottom equation by 3. We get 6x minus 3y equals 18. And then we could add the two equations, and the negative 3y and the positive 3y would cancel out. And that would allow us to solve the rest of the problem with just the x's in the equation. So graphing is a little bit different. It's just you plug it into a calculator and you see where they intersect. Substitution and elimination, the important thing to note is the thing you're trying to do is end up with an equation where there's only one variable, because you can't solve an equation where there are two variables and constants, right? You need to have only one variable. So whether it be through substitution or elimination, as long as you're getting to a state where there's only one variable in your equation, that's going to allow you to solve the question. So this is kind of a review of the background of systems of equations. How does this inform your test day strategy, right? So it's, again, important to note, it's not just about getting the right answer, even though that's the number one most important thing. It's about getting there as quickly or as efficiently as possible. So some questions will tend to be more easily solved by one of these strategies than the other. Some, for example, in substitution here, if it's already set up this way, then you don't have to go through the process of isolating y. You can just plug it in. This question is more well suited for substitution. Could you solve it through elimination? Absolutely, right? But it would take more setup time. It would probably take you longer to get to the right answer. Whereas if you just kind of do it the path of least resistance, solve it the most efficient way, that would make the most sense and be the quickest. Now, if you find that there's one strategy you're more comfortable with than the other, that might be a different story. I would recommend trying to do a lot of practice. You can find worksheets about systems of equations online just to get comfortable with those strategies. But again, both of these strategies will always yield you the same solution. Just the amount of work that you have to do to get there might be a little bit different. Okay, so that's how you solve systems of equations. Let's see how we see these concepts tested in an actual SAT question. So taking a look at the equation to the left, what is the solution to the system of equations above? We have negative 2x equals 4y plus 6, and 2 times 2y plus 3 equals 3x minus 5, right? And so what they're really asking for is what is the solution in x and y to this equation? So taking a look at this, we want to say, okay, well, which one of these strategies that we just identified on the last slide, graphing, substitution, and elimination, are the most effective for this question? And so for here, I would say substitution seems to be the best bet, both because x is already standing by itself on the left side, and then also, as we're about to see, it's here we're allowed to do kind of an unconventional substitution, where if we simplify negative 2x equals 4y plus 6, this top equation, and we divide by 2 instead of negative 2, we get negative x equals 2y plus 3. And we can see here is that 2y plus 3 exists as a full term in the second equation. So instead of substituting in for x, we're substituting in for 2y plus 3. And so we can plug in anywhere on the second equation where the term 2y plus 3 occurs, we can switch that out for negative x. What does that look like? That's going to give us 2 times negative x equals 3x minus 5. Right? And so here we can multiply out. This is, again, notice how we've gone from a system of equations to what we would essentially call, from the beginning of the presentation, a basic linear equation where you have one variable and you're just trying to isolate it. So you have negative 2x here, you can add that to 3x, that's 5x, and then you add 5 to the other side, so 5x equals 5, and we get x equals 1. So sometimes if you take a look at the answer choices and there's only one answer where x equals 1, then you can just pick that one. In our case, we are not lucky enough to have that. We see we can eliminate C and D, but we still have either A or B, whether or not y equals 2 or negative 2. So we'll continue solving the question. We see if we plug x equals 1 back into the first equation, we get negative 2 times 1 equals 4y plus 6, and that equals 4y minus 8 if we subtract 6 from both sides, and then finally y equals negative 2, right? And so our full answer choice is going to be x equals 1, y equals negative 2, and that will give us b. So again, this is a system of equations. We identified the easiest or path of least resistance approach to this question, and we were able to take a kind of unconventional approach where instead of substituting in for x, which is what we would normally do, we were actually substituting in for 2y plus 3. Now, if you didn't notice that this was something you could do, that's totally fine. Could you solve it by substituting in for x? Again, absolutely, right? Could you solve this equation through elimination, right? If you reset this equation so that both variables are on the same side, could you solve it that way? Absolutely. The question is, that process, how much longer would it have taken you? And so ideally, if you could solve it this way, that would save you the most time. And again, just making sure you're comfortable handling the kind of different substitution, the manipulation of these equations, that's going to prepare you the best for solving systems of equations questions. Okay, so we'll move on to another kind of aspect of systems of equations, which is saying how do these equations look when you're talking about graphing them, or graphically what do they appear to be. And so the conventional solution we think of when we graph a system of equations is that they will intersect, right? And that point of intersection is the solution to our system. Most cases, that's what will happen. However, when we're given a system of equations that is in most cases and doesn't have a unique solution, there are two other things that can happen. The first thing that can happen is that instead of intersecting, the lines are parallel. And because the lines are parallel, meaning they have the same slope, the system has no solution because the lines never intersect. If we have two perfectly parallel lines, they're never going to cross, right? And so that system of equations will, if we tried to solve it, would never have a solution and never yield a solution. And if we graphed it, we would just see two parallel lines. In the second case, that's not the parallel lines, we would see that the lines could also be identical, in which they are the exact same equation, they overlap on every single point, and if you graphed it, it would just look like a single line. And what that means is that every single point on either line is a solution. And so this system, instead of having one unique solution or instead of having no solution, has an infinite number of solutions because they overlap on every single point, right? And so this is, again, something you might have seen in the math classroom, but can be easily demonstrated if we take a look at what they look like graphically. So we have our most common case of systems of equations, intersecting lines. You give me a system of equations, oftentimes it's going to have that unique solution, x, y, whereas these two lines intersect. You have our first less common occurrence, which is a parallel system of equations, where, as we can see, there's no points in common because these lines will extend parallel to each other indefinitely without ever touching each other, without ever intersecting, and so there will be no solution. And then you also have your coincident lines, which is our overlapping lines, where we say, okay, well, I'm graphing this. I thought I had two equations. There only seems to be one line. That's because the lines are exactly the same and they intersect each other. What that often means is that the equations are simply, one equation is simply the other equation multiplied by a constant. And so that would give us a situation where you would have coincident lines. And again, the way we interpret this is that there are infinitely number of points that these lines have in common, since they intersect at every single point along the graph. And so that means every single point is a solution, and therefore we have an infinite number of solutions. Okay, so hopefully between the explanation here and the graphical explanation here, it's pretty clear what we can expect to see when we have a graphical system of equation. We can again see how this relates to the other solutions we took, like elimination substitution, if we look back to the exact same problem that we used for the other equation over here, right? So this is our system of equations from before, and simply saying, if we wanted to graph this, what would it look like? Well, if we put this into a calculator, we would get this graph on the right-hand side, and that would give us an intersection point of 1, -2, which is the same answer we did here on B. Now, again, I would suggest most likely doing the algebra. That would be faster than isolating this into a format that is compatible with a graphing calculator. Oftentimes, for a system of equations question, you might not even see it on the calculator section. So this is more so a visualization of how all these concepts relate, right? If we wanted to solve the system of equations with a graphing approach, we absolutely could, just like we could solve it with both a substitution approach and an elimination approach. And so here we can see an example of how this system of equations is tested in terms of understanding the different scenarios that can happen on the coordinate plane. So this question says, we're given a system of equations, 2y plus 6x equals 3 and y plus 3x equals 2. How many solutions does the given system of equations have? And so looking at the answer choices, we can have 0, exactly 1, exactly 2, infinitely many. Important to note, if these are both linear equations, there's no way it would be 2, so we could eliminate that already. But we could do this algebraically, where we say, okay, let's do elimination, because these are in a very, very similar structure. We can multiply this second equation by 2. We get 2y plus 6x equals 4. And then suddenly, we see a problem. We see 2y plus 6x equals 3 on the top, and then we have 2y plus 6x equals 4 on the bottom. So how is it possible that these two equations with the exact same terms on the left-hand side equal two different constants? That solution tells us that there should be no solutions to this question, because there's no way that would happen. And so we could also graph this and see, again, these lines would be parallel and therefore have no points of intersection. With that graph telling us the same scenario, again, we would say there are no solutions. So we can see we can do any of these approaches to solve the same problem. As you can probably see, graphing this would have taken more time than us just doing the elimination approach, where we say, oh, well, that doesn't make sense the way that we have it set up. Okay, hopefully that makes sense, and we've gone over this example as well. So we can also test see on the SAT a slightly different variation of the system of equations questions, and that's based on not just solving the equation, but understanding the relationship between these equations so that we can solve for other constants. And so let's take a look at this question here. It says, in the system of equations above, a and b are constants. If this system has infinitely many solutions, what is the value of a? So our system says 3s minus 2t equals a, and negative 15s plus bt equals -7. So the key point or key piece of information given to us in this question is that the system has infinitely many solutions, which we just said means that these two equations must be identical. What we also touched upon was that normally when you have a system of equations where you have infinitely many solutions, it's common for one problem or for one equation to be the other equation multiplied by a constant. So we can see here that that's most likely the case. This is again the thought process we just went through. They must be equivalent. And so we know that we have these two equations in the system of equation in roughly the same form, right? It's constant times s plus constant times y. Constant plus s. Constant times s plus constant times t equals a constant, right? And so that's the equation that both the first and the second equation follow. And we say, okay, if we get both these terms to be equal to each other, then we know that the constants must be equal to each other as well. So for us, the most apparent thing is if we multiply the top equation by -5, we would get the term for s to be the same, and therefore we would know the terms for t and the term on the right would also have to be the same. So we can go through that process. We multiply the top by -5, we get -15s plus 10t equals -5a, and then we can go through a basically comparison, or this would be almost elimination of the constants to tell us what are the values of a and b. So we have the constants for s are both -15, and that tells us the constants for t must be the same, which means b equals 10, right? Because if it's 10t up here, it must be 10t on the bottom. And finally, we have -5a is equal to -7. We can go through the solution for that. -5a equals -7, that means a is equal to 7/5. Going back to the question stem, if this system has infinitely many solutions, what is the value of a? And so a is 7/5, and that would be the final answer to this question. The way this question is set up, it could be a gridding question. We could definitely be asked to put this into the student-filled response section just because it's not giving us any multiple choice options. But again, seeing that this wasn't just asking us to solve a system of equations, but it says, given the relationship that we are telling you exists in this system of equations, what are some other things you can identify? And you can see how the key step here is knowing that a system of equations which has infinitely many solutions means that these two equations must be the same. That's the key step and key piece of knowledge that we need to have. So hopefully that makes sense, and we can see how the knowledge that we gained from talking about the system of equations and their relationship can be applied to the type of question we see here. And then again, when we're talking about the relationships between lines and graphs, there are key kind of concepts relating to the slope relationships between systems of equations when they are in unique configurations. So let's assume that we have lines L and K, which are both defined, and we're given that these two lines are parallel. What that tells us is that basically both lines have the same slope. That makes sense. They're both basically heading in the same direction at the same angle for infinity, and so by definition they must have the same slope. And the other kind of relationship or configuration there might be is that you're told that line L and K are perpendicular, and that is a more unique configuration in which the two lines intersect at 90-degree angles, and that tells us that the product of their slopes must be -1. This is also commonly taught as the slope of two lines that are perpendicular to each other must be direct inverses of each other. So if the slope of one line, let's say line L, is 2, then the slope of K must be 1/2 times -1, so -1/2. And we can see that 2 times -1/2 would equal -1. So either of those ways of remembering it would work. And these are just our two kind of more unique configurations of lines. So how might this be tested on a SAT math question? So we can see here that this graph is given to us in the coordinate plane, and we say that this is a graph of line K in the XY plane. Which of the following is the equation of a line that is perpendicular to line K? Again, this question, I don't think I would say is the most commonly tested type of question, but you should not be surprised to see a question testing this concept. And so what we just talked about in the last slide is, well, if we have two lines that are perpendicular, then the product of their slopes must be equal to -1. And so the first thing we have to do is say, okay, well, what is the slope of the line K? And that we would go to the slope equation, which is m equals y2 minus y1 over x2 minus x1. We can use some of the clearly identifiable points on this graph. College Board was nice enough to give us a graph where there are clear intersection points. We can use 0, 6, and 3, 0, plugging that into the slope the slope equation, we get 0 minus 6 divided by 3 minus 0 equals -2. That fits with the slope of the line that we see here. And so we know that the slope of a line that is perpendicular to line K is going to be the inverse of -2, or whatever multiplied by -2 is going to equal -1. And so we can say, well, -2 times -1 is 2, and 1 over 2 is 1/2. And so the line that is perpendicular to line K is going to be equal to 1/2. And so taking a look at the answer choices given to us, we can see that only one of these answer choices gives us an equation with a slope of 1/2. That would be answer choice C, y equals 1/2 x plus 3, and none of the other answer choices satisfy the relationship between the slopes of two perpendicular lines, and therefore we would pick answer choice C. Hopefully that makes sense. Again, the key kind of piece of information that you needed to answer this question was to know that there is a relationship between the slopes of two lines that are perpendicular. That relationship is that their product is equal to -1, and that piece of information allows you to solve the rest of the problem. So again, being comfortable in remembering that information is going to be really important for taking some of these, solving some of these questions. Okay. So one of the last concepts that we'll go over in this section is going to be about slope-intercept form. That is basically any equation that you see that involves a linear equation where it's set up as y equals mx plus b. I think one of the core processes that students should be familiar with when dealing with slope-intercept form is simply, if you're given 2 points, you should be able to write out the line that connects those 2 points or intersects through both of those points. And so this is really just a two-step process, right? If we look at the equation here, there's only 2 constants that we're solving for, m and b, where m equals slope and b equals your y-intercept. For those of you who are still need a refresher for slope and y-intercept, slope is saying for every 1 unit change in x, how much is y changing by? That's going to be given by the slope rise over run equation, m equals y2 minus y1 over x2 minus x1. And then b is your y-intercept, which is essentially saying if x equals 0, what does y equal? Or put another way, where does the line cross the y-axis at? And so that we would see more easily graphically. So our two-step process is saying, okay, well, first let's solve for m, which is the slope. And given 2 points, we would just use the slope equation, plug that information in, and we get m. Now we're left with y equals mx plus b, where we already know m, but we don't know b. And so in order to get b, we would take either of the points that we are already given that we know exist on this line that we're trying to find, and we would plug in those x and y values into our semi-solved equation. So we plug in x1 for x, y1 for y, and we just solved for m. That means 3 out of our 4 variables are basically constants, and we're just left with our one variable b, which is our y-intercept. And we can solve for that pretty easily, and that's going to give us the y-intercept value. Put it all together, we get y equals mx plus b, and now we have a a slope-intercept form of an equation which intersects both of the points given by the question, right? And so I think this is the most easily illustrated through a example. So let's take just 2 random points, -4, -7, and -6, 9. And let's say we want to find the slope of the equation that crosses both of these lines. The just overall equation that crosses both of these lines. So again, our step 1 is saying, okay, let's find slope. So slope is given by y2 minus y1 over x2 minus x1. So we have 9 is y2 minus y1, which is -7, divided by x2, which is -6, minus x1, which is -4, and we're given this equation here. So 9 minus -7 is 9 plus 7, so 16. -6 minus -4 is -6 plus 4, so -2. We get 16 over -2, and we get a slope of -8. So that's our step 1, right? Fairly simple. Is it important? Some students are sometimes confused. Does it matter which one of these points is x1, x2, and sorry, which one of these points is x1, y1, and which one of these points is x2, y2? And the answer is no. You could easily do this the other way around and flip it. The only thing that's important is that you're identifying each point similarly. So if this is x1, then this has to be y1. If this is x2, then this has to be y2. That's the most important thing. We can see if we flip that, we have -7 minus 9 would equal -16, and -4 minus -6 would be -4 plus 6, so 2. So it would be -16 over 2. We would still get -8 for our slope, right? And so that process is the same no matter what. So no need to get tripped up on, oh, well, I'm not sure which point is 1 and which point is 2, right? Those are interchangeable as long as you're keeping it consistent. So we have our m solved for, so we can plug that in for our m in our slope-intercept form, y equals -8x plus b. And then the second thing we can do is say, okay, step 2, let's find out what our y-intercept is. We can plug in either of these points into our graph. Let's just take this -4, -7 point. So y is equal to -7. So -7 equals -8, which is our slope, times x, which is -4, plus b. So now, again, we see we went from an equation which has three variables to an equation which has one variable, just b. And we can say, okay, let's solve for b. We get b equals -7 minus 32, which is -8 times -4, and we get -39. So now we should have all the information we need to assemble our equation into the final product, and that's going to be equal to y equals -8x minus 39. And that is the slope or equation of the line that intersects through both -4, -7, and -6, -9. I think that this is a good test of kind of your how comfortable you are with some of the basic algebra in linear equations. If this is something that is confusing to you, that's no problem at all. The best solution to that is just to practice. If you can go online, you can say slope-intercept worksheet. There will be tons and tons of practice problems that you are going to be able to do that will help you be more comfortable with this process of solving. I don't believe that you will often see a question which simply says find the intersection, the line that intersects between these 2 points, and they just give you 2 points and you do this process. However, there are going to be a lot of questions that build on your ability to do something like this. Let's say, for example, they give you an equation and say find the y coordinate of one of the points that this line goes through. So again, as long as you're comfortable with this process, you should be able to answer any variation or application of this process, and this will give you a really good foundation to solve some of these SAT problems. So, I understand this is maybe for some of you something you're already very comfortable with. That's great. Make sure you know how to do that to the level in which you can adapt whatever your strategy you're taking to the specific question that College Board is designed to test this concept. Okay, so putting that aside, that should wrap up kind of the basics of our linear equation section. And what we basically can move on to is translating of word problems. Now, you might be asking, what do I mean when I'm referring to algebraic word problems? And so on the SAT, and we'll see this in the examples that we're moving through, what we're often going to see is that there are questions in which it's not a straightforward type of question where an equation is given to you or a system of equations is given to you and you solve for something or you derive something or something of that nature, right? Which is kind of what we're used to seeing in a math classroom, right? Give this equation, let me solve it. College Board, especially recently when they're designing their tests, they're really interested in not just saying how comfortable are you with math, but how comfortable are you interpreting a question so that you can get to the point where you need to use your math skills, right? And so that's going to be giving you scenarios in which it's not that straightforward. It's a problem set up in a scenario or real world context, and how do you translate that into a equation or system of equations where you are more comfortable doing the math. So we can give an overall strategy of how you approach these types of word problem questions. So this is just a simple strategy you might have seen online, and it simply says in a 4-step process, here's how we'll approach every question we identify as a word problem. So the first thing we want to do is define excuse me, is define variables and choose letters that make sense. If it's a variable that represents dogs, choose D. If it's a variable that represents cats, choose C, right? Like, as long as it's clear and easy for you to understand, there's no rule that you have to stick with X and Y, right? And so define a variable and choose those letters that make sense, and just remember and make it easy to remember what each letter of the variable represents. The next thing you want to do is break these sentences into short phrases and translate each of those phrases into an actual expression. And finally, when we've translated all the individual phrases, we can put those expressions together to form an equation. So the easy things to kind of note is that there are a lot of ways to say relationships between concepts that are pretty clearly defined in math. So equal sign, if we see an equal sign, we automatically know what that is. But in a word problem, there's a lot of ways you might see that. You might see is equals to, is equivalent to, is, was, will be, the same as much as. So all these things we just have to remember that means equal to, and we would write that out in our little translation of that phrase. Plus can be plus added to, sum combined. Minus can be subtracted from, decreased by. The difference between, multiply could be times, product of, twice, double. Divided by can be out of, each, ratio. And then a variable can be a number, how much, how many, or what. And so this is going to be up to you to define what that variable is. But we can again see here that, math is fairly straightforward. You give an equation, you know all the relationships. English can be a little bit more convoluted, and our job is to move from the English back to the math, because at the end of the day, this is what we're trying to deal with, not this stuff, right? So we use that strategy to approach those questions. So in terms of word problems, this is kind of similar to what a conventional word problem might look like. So we can see it's a block of text, right? Some numbers in between, but it's not as clear as just here's an equation, right? And so the way that I've kind of chosen some of these questions for this section is to say what, even in some of the same word problems, what are some of the different ways in which we can do some of them, be asked to solve for different things, right? So let's take a look at this first question here. So in 2014, country X had 783 miles of paved roads. Starting in 2015, the country has been building 8 miles of new paved roads each year. At this rate, if n is the number of years after 2014, which of the following functions gives the number of miles of paved roads that there will be in county X? Assume that no paved roads go out of service. So this is, I think, the most straightforward word problem that they'll ask for, is say, how do you translate this block of text into a equation, right? So our first step, remember, was we're saying we're going to define some variables, and we're already given some variables they've defined for us, and that's n, which is the number of years after 2014, right? And so we can go through this entire process of breaking down the solution. So if we define n as the number of years after 2014, as is given in the question, we can get define m as the miles of paved road that exists in a given year, right? And so that's something that we did not get defined for us in the equation, but that's something we will want to define for ourselves. And so taking a look at this question, that would be equivalent to f of n, right? And so what are the kind of different pieces of information that we need to piece together here? So we have the first year in year 0 in 2014, the county already had 783 miles of paved roads. So if we think back to our discussion of slope-intercept form, what we can basically say is that 783 is our slope-intercept, is our intercept, our y-intercept. When n equals 0, the county already has 783 miles of roads. They don't have to build any more. It has been 0 years. There's been no time has passed, and we already have 783 miles. So that's going to be our y-intercept. So that'll be b. And then the next thing we want to know is, what is the slope? So for every year that passes, as n increases by 1, how much does m increase by, or how much does f of n increase by? And so we're given the rate is that in every year, the county builds 8 miles of new paved roads. And so that would say our slope would be 8. And so m equals 8, b equals 783. We put that together and we get our overall equation for this question. And that is f of n equals 783 plus 8n. And we can see that that's the only equation that really satisfies that function, and that's the one we would choose to represent this word problem. Okay, so hopefully that process makes sense. Again, like I was talking about before when we were discussing slope-intercept form, it was really helpful to see that we're comfortable with the structure of y equals mx plus b, so that we can interpret that given the information that we have in this problem. The other thing that we can see is that when it comes to word problems, you could be asked a lot of different things given the setup of the problem. It's not necessary that they just ask you for the interpretation of the equation. So that goes into the second problem. So the first problem says, give us the equation that represents this scenario. This problem is the same setup, but it says, at this rate, how many miles of paved roads will County X have in 2030? So that's not the same end question stem that we had in the initial problem. And we can see here, we could use the same equation that we saw in the first setup, which is m equals to 783 plus 8n. And we say, okay, well, we have this relationship already identified. And we go through the same thought process that we did for that first step. What's the next step, right? And so the next step is saying, how do we use this equation? And so if we're saying how many miles of roads will County X have in 2030, what we have to know is how many years have passed between now and 2030. So that's basically solving for n. And we can say between 2030 and 2014, there were 16 years that passed. And in those 16 years, every year, 8 miles of new paved roads were built, and that's represented by plugging in 16 to our existing equation. So we have m equals 783 plus 8n is now equal to 783 plus 8 times 16 years. And that gives us 911 miles. And so our final answer would be 911 miles of paved roads in 2030. For us, again, we can see here that once we got to the interpretation, once we have the equation, this is a very straightforward question, right? Imagine if this equation were given to you and they said m equals 783 plus 8n and assume n equals 16, right? That's something that you'll be able to probably solve very quickly and very comfortably. So the challenge with word problems is not the math usually. The math is usually simpler because there's already added difficulty from it being a word problem. The challenge is that we need to get from the word problem to the equation. And so that is what we kind of handle with this kind of scenario in the problem. So let's take a look at another way in which we might see the word problems, the same context being tested. So in this case, we still have the same context. It says in 2014, County X had 783 miles of paved roads. Starting in 2015, the country has been building 8 miles of new paved roads each year. And now we have a different question stem again. And it says, well, given this scenario, given this context, at this rate, in which year will County X first have at least 1,000 miles of paved roads? And we assume that no paved roads go out of service. So how do we approach this question? Just thinking abstractly, we would approach it the exact same way we did before. The first step is still translating this context. And we've done it before, so it's easy. But if this was the first time, we'd still say, well, our B and County X at 2014 at year 0 has 783 miles. That's our B. That's our slope, our y-intercept. And if the rate at which they're building roads is 8 miles, that's our slope. We still have y equals 8x plus, m equals 8n plus 783. And now the question is, how do we use that equation that we have that represents this scenario to solve this question? And hopefully your inclination is to say, okay, well, we just have to plug in 1,000 miles for m, because we're looking to solve for n, which is the year in which this county is going to have their at least 1,000 miles. So we can put that in, and that's going to be an inequality, right? And so we have that exact substitution goes on here. 783 plus 8n is greater than or equal to 1,000. So m is no longer in the equation, and we have a scenario or an inequality where we only have one variable that is unsolved for. And that variable is n, right? So we can manipulate this inequality the exact same way we would manipulate an equation. Subtract 783 from both sides. We get 8n is greater than or equal to 217. And then 217 divided by 8 is equal to 27.125. Now, the important thing to note here is that there's the setup in the question stem says is not exactly what point in time will there be 1,000 miles of paved roads, but more so how many, what is the first year in which the country will have at least 1,000 miles of paved roads, right? And so if we round, we basically have to round this equation up to 28, right? Where we know that n at any point in time after 27.125 years is the exact point in time in which they reach 1,000 miles. But the first full year in which they have at least 1,000 miles is going to be year number 28. And so if we add 28 to 2014, we get 2042, and that's the final answer, right? So I think this is a good point in time to point out basically an important way that you should be approaching these word problems, and that's to make sure at the end you're always double checking to make sure you answer the question, right? There are several different things that could have happened here which might have led us to choose the wrong answer if this was a multiple choice or plug in the wrong answer. For example, let's say we didn't go back and we didn't reread the question stem and we didn't realize it says in which year will County X have at least 1,000 miles of paved roads. What if we just assumed it was in how many years? So then we just plug in 27.125 and we assume that's the right answer when we move on. Well, that's not what the question was asking. That's going to be the wrong answer. And so we went through all this process of getting to this final answer and we plugged in the wrong one, not because we made any mistakes or not because we didn't know how to do the problem and not because we couldn't even answer the correct problem. It's just we read the problem wrong the first time, right? So double checking can save us a lot of that time. Again, let's say at this rate, in which year will County X first have at least 1,000 miles of paved roads? Maybe we interpret that as saying, in which year is County X going to have exactly 1,000 miles of paved roads? So then we might round down and we say, oh, it's 27, it will be 2041. Or we might say 2041.125. Any of those answer choices would be wrong, right? 2042 is the only correct answer choice here. And so that's why it's really important for us to go through that process of not just read the equation, read the question, interpret the question, solve the question, also double check at the end. Just last 4 or 5 seconds could save you from making an error that costs you the point, right? And so it's really important to be paying attention to those details and making sure we get the point that you honestly deserve if you've done all this work. Right, so let's take a look at another word problem that you might see. So I think we're moving away from the scenario that we were talking about building roads, and we're going to talk about this question here, which again might be a little bit less straightforward than you see on first glance. So the question says, to edit a manuscript, Miguel charges $50 for the first 2 hours and $20 per hour after the first 2 hours. Which of the following expresses the amount C in dollars that Miguel charges if it takes him X hours to edit a manuscript where X is greater than 2? So for us here, what we really see is that we're dealing with this translation process, and there's a little bit more, I guess, trickiness involved in this problem, right? So taking a look, we say that Miguel charges $50 for the first 2 hours and $20 per hour after the first 2 hours. So what we can say is, well, we're trying to solve for the slope. Is the slope $25 per hour if it's 50 for 2 hours, or is it $20 per? Is the slope 20, where every hour costs them 20? And so that's kind of a little bit confusing because we don't know what we're supposed to do here. And so what we want to say is the long term. What is the long term rate, especially if we're assuming x is greater than 2 over, let's say hours is thousands of hours. How much is he getting paid per hour? How much is he charging per hour? And the answer there is $20 per hour, right? And so then the question is, okay, well, is he charging $20 times X? Or is there an exception because there's a different charge for the first 2 hours? And the answer is, yeah, there's a different charge for the first 2 hours, so his rate is going to only start after 2 hours. And so that gives us X minus 2 hours as the term that he is charging $20 per hour for. So we can write that as saying, okay, well, his initial start point is going to be $50 for the first 2 hours. So 50 plus 20, which is our slope, times X minus 2, because his rate of $20 per hour only starts after 2 hours have already passed, right? So if 2 hours have passed, then his total charge is $50, which satisfies that first part of the question. And if his total time is 3 hours, then he makes 3 minus 2, so 1 hour. In that 1 hour, he charges $20. So that kind of process allows us to get to this final equation here. So we can take a look at the equations given to us in the multiple choice, and we see that, hold on, none of these equations seem to be right. They're all different than the one we have. So that's because we haven't fully simplified yet, right? So we can go through the process of multiplying out 20, and we get 50 plus 20x minus 40. Simplifying that, we get 20x plus 10, and we can go back to our answer choice and compare that to the answers, and we get B as the correct answer. So again, looking back on this question, the important thing for us to realize was, okay, there are some nuances in this question where it's not just, let me just write down and translate this directly, right? So we have to do some adjustment because of this different rate in the first 2 hours versus the rate after 2 hours. Once we do that adjustment, again, it becomes easy as soon as we do a translation, right? This word problem challenge, again, of translating, once we overcome that hurdle, then we're kind of in the home stretch where we have 50 plus 2x minus 40. We solve that. That's very, again, similar to the linear equation problems we were doing in the first half of the session today. So hopefully that makes sense, and we can see how we got to this final answer of B. Okay, so let's take a look at another question, which we might ask probably in a grid-in response, and essentially asks us the following. A builder uses the function g given by g of x equals 80x plus 10,000 to estimate the cost in dollars to build a one-story home of planned areas of x square feet. If the builder estimates the cost to build a certain one-story home is 106,000, what is the planned floor area in square feet of the home? And so looking at this type of question, it's fairly straightforward in that we're not going to be doing too much translation, right? The function g of x equals 80x plus 10,000, that's already given to us, which is great, right? So we're not having to deal with pulling all those pieces of information together to come up with a final answer. If the builder estimates, so if the next step is saying, okay, so what are we trying to find here? So we go back to the question and says, if the builder estimates that the cost to build a certain one-story home is 106,000, well, that means we can substitute something in, right? G of x is the cost it takes to build a one-story home. So we substitute in 106,000 to this equation, and we get the following. G of x equals 80x plus 10,000 equals 106,000. Again, once we've gotten to this point in time, it's very simple to just do a linear equation and solve for the variable. Subtract 10,000 from each side, you get 80x equals 96,000, and you get x equals 1,200. And so in that sense, this problem was a little bit easier than the rest because less translation was involved. We get to the final answer, x equals 1,200, and that should make sense to us. The process here is a little bit more straightforward than some of the problems we were dealing with before. Hopefully, again, this makes sense. We can see that you know, most of the time once we get to the actual linear equation that we solve for in the word problem, that's going to be a lot easier than some of the stuff what we're dealing with in linear equations or systems of equations, or a passport to advanced math sections or categories. Okay, let's take a look at this question here. So this question here is going to test our knowledge of not just translating word problems to linear equations, but translating word problems into systems of equations. So let's take a read through. Maiza bought a pair of pants and a briefcase at a department store. The sum of the prices of the pants and the briefcase before sales tax was $130. There was no sales tax on the pants and a 9% sales tax on the briefcase. The total that Maiza paid, including the sales tax, was $136.75. What was the price in dollars of the pants, right? So we can kind of already see in our head the way that this system of equations is going to come together. But basically we want to say, what are the different relationships between the different variables given to us in this equation that we can write out into an actual system. So let's go with that second sentence. The sum of the price of the pants and the briefcase before sales tax was $130, right? So we can create some variables that represent our two things that we're talking about. So P is the price of pants and B is the price of briefcases. Putting that together, we get P plus B equals 130. Hopefully that kind of makes sense. If the price of the pants together and the price of the briefcase together before sales tax was 130, then together P plus B equals 130. The next thing we want to say is, okay, these are P and B are both pre-sale tax. What are the other relationships that we can identify? So if the total that Maiza paid, including the sales tax, was $136.75, and we know that there is no sales tax on the pants and a 9% sales tax on the briefcase, what does that look like? So no sales tax on the pants means it's just still P. The post-sale tax is the pre-sale tax. The post-sales tax price is the pre-sales tax price. So it's still P. And then a 9% sales tax on the briefcase is equal to B, which is the pre-sales tax, plus 0.09 times B, which is the sales tax add-on, giving us 1.09B. So together, we would get P plus 1.09B. So the post-sales tax of the pants plus the post-sales tax price of the briefcase is equal to 136.75. And now we have ourselves a real system of equations. Putting this together, we have our first equation is P plus 1.09B equals 136.75, and the second equation we have is P plus B equals 130. How do we go about solving this? Well, we can do substitution, we can do elimination. For us, it's probably easiest just to do elimination, and the reason we say that is because we can just eliminate P immediately by subtracting the second equation from the first equation. So P minus P is 0, 1.09B minus B is 0.09B, and 136.75 minus 130 is equal to 6.75. Putting that information together, we get 0.09B equals 6.75, or B equals 75. Going back to the stem, are we done yet? It says, what was the price in dollars of the pants? What did we calculate? We calculate the price of the briefcase. So we want to put the information we have here, the price of the briefcase was 75, into our second equation. The sum of the prices was 130, and we get P equals 130 minus 75 is equal to $55. And so that is our final answer. The price of the pants was $55. Again, the process here would not have been challenging if we had been given this system of equations right off the bat, right? If the question says, here's two equations, solve for P, I think a lot of you guys are definitely going to be able to solve for that, especially when the numbers are fairly straightforward. The challenge is translating from the question stem, which didn't give us any straightforward equations like the last question, into this format in which we're able to answer the questions in the system of equations format, and that gives us the final answer. So again, make sure you're comfortable with systems of equations. Obviously, that's very key to solving this question, but when it comes to word problems, make sure you're comfortable translating those questions accurately this points accurately into the final product of the question. So let's take a look at this question here. It says, each morning, John jogs at 6 miles per hour and rides a bike at 12 miles per hour. His goal is to jog and ride his bike a total of at least 9 miles in no more than 1 hour. If John jogs J miles and rides his bike B miles, which of the following systems of inequalities represents John's goal? So let's take a look and pause and say, let's take a look at the answer choices. The answer choices here, we're all given, we're not solving for anything, we're just saying, how do we translate this into a system of inequalities that represents his goals? And so the key, I think, equation we need to keep in mind here is something that hopefully you guys are familiar with, but I know even when I was studying for the SATs, that was kind of the root challenge for me. And that was the relationship between distance, rate, and time. And so the information you really need to know here is distance equals RT, or D equals RT. So the equation that we have here, keeping that in mind is going to make it a lot easier to solve for this inequality relationship. So John jogs J miles and rides his bike B miles. His goal is to jog and ride his bike a total of at least 9 miles, and that inequality is represented as J plus B is greater than or equal to 9. The reason that makes sense is because if J represents the amount miles he jogs and B represents how much he rides his bike, then he wants to ride at minimum 9 miles and at most anything greater than 9 miles. So that would be that inequality here. And this, again, we can see eliminates question choices B and C because they don't match up with the inequality we've set up here. So then we keep in mind this rate and time equals distance, so D equals RT relationship. And so we want to say, okay, we've already have the distance equation. We know the relationship between his goal and how many miles he wants to do overall. The other thing we want to do is saying, okay, he wants to do it in no more than 1 hour, and we know the rate at which he rides his bike and jogs each mile. So the time he jogs is going to be equal to J miles, right? The total distance that he runs, divided by 6 miles per hour, which is the distance, the rate, and that's going to give us the time, right? Distance over rate equals time. So J over 6 hours is the total time he jogs. And then we can do the exact same process for the biking portion of his miles, right? So again, if we say, well, rate times time equals distance, that means time equals distance divided by rate, then time is going to be equal to B miles divided by 12 miles per hour, and that's going to give us B over 12 hours. So putting those two pieces of information together, we know that John wants to jog. John is going to spend J over 6 hours jogging, and he's going to spend B over 12 hours biking, and together that should take no more than 1 hour. So added together, J over 6 plus B over 12 should be less than or equal to 1. And therefore, putting that information along with our original equation of J plus B is greater than or equal to 9 is going to give us answer choice A. Now I understand that this is a difficult question. The relationship you really want to keep in mind here is that between rate, time, and distance. This is one scenario in which knowing that is going to make your life a whole lot easier. There are a ton of other types of questions which are not even necessarily going to be word problems, which are going to test your knowledge of the distance of the relationship between rate, time, and distance. And for me, I remember that was a big point of confusion, and I think the way you solve that is just do more practice problems, become comfortable with that relationship, know that you can manipulate this equation so that any type of relationship can be identified, whether you're trying to solve for rate, whether you're trying to solve for time, whether you're trying to solve for distance. That's going to be something to keep in mind. Hopefully, once you have those relationships in mind, it becomes a lot more clearer what kind of calculations for the inequalities in your system are going to look like. We know that one of them is going to be for miles, for distance, and we know that one of them is going to be for time. Doing that calculation is pretty straightforward once you have those relationships in mind. Now, hopefully, that's going to be something that you guys are comfortable with, and definitely I understand that this word problem can be a little bit trickier. I know a lot of students think that this one's a little bit trickier than the rest, so don't worry at all about that. If it's still a little bit confusing, definitely revisit it and just do some more practice problems testing this D equals RT relationship. Okay, so let's take a look at this word problem here. And so we can see that it says a voter registration drive was held in town Y. The number of voters V registered T days after the drive began can be estimated by the question V equals 3450 plus 65T. What is the best interpretation of the number 65 in this context? So again, we can see that this word problem, again, all these problems that we've talked about today are word problems. The question is, how is the word problem, what concepts are word problem testing? The previous word problems have tested their ability to manipulate the equations or translate the equations. This one is saying, how do we interpret specific components of an equation that is already given to us? So giving us here, we can intuitively say that 65 should be equal to the slope, right? If this is equation in slope-intercept form, y equals mx plus b, 3450 is b, 65 is m, t is x, and v is y, right? So 65 should be the slope. And that would mean that for every day after the drive began, 65 additional people register. The number of voters, so looking at the answer choices, that should tell us that 65 is the number of voters registered each day during the drive. Now, if we don't want to, so that's how I would think of it. If you're comfortable with the slope-intercept form, I think that's a very intuitive way of thinking of it. If you don't want to think of it that way and you want to look at this in what we would call the marginal case, we can actually do some calculations to test for what this relationship would be. In the given equation, when t, which is a number of days after the drive began, increases by 1, v, the number of voters registered, becomes t plus 1. So we can add this marginal change of 1 day into the equation. So instead of saying v equals 3450 plus 65t, we can do v equals 3450 plus 65t plus 1. And so solving that out, we can multiply 65 into both terms. We get 3450 plus 65t plus 65. So what did we just see happen? We saw that if we change the number of days by just 1, we add just 1 day after the drive began, then v, the number of voters, has increased by 65. Now, to me, that is essentially the definition of the slope, right? And so you would just get to the same conclusion at the end, which is saying 65 is the number of voters registered each day during the drive. It's just two different ways of getting to that interpretation. One way, you go with the basic definition of a slope and you interpret it that way. And the other way, you can do this marginal definition of what the change in t results in. And that's going to be the same answer, choice D. Again, this is still a word problem. It's testing how comfortable we are with the concepts being given to us, not just in equation format, but also in a more word-heavy context, right? So a lot of students I've talked to are kind of intimidated when they see a word problem. They'd much rather have just an equation to solve. My advice is, again, don't treat it as a word problem. Treat it as just a algebraic problem that requires one further step of translation, right? And so we can work on that. We can use the same strategy or approach we talked about in the beginning of this section, which is that 4-step approach. And again, the best thing you can do is just make sure you also have a solid foundation in the algebraic concepts, because once you go through a translation, then you should be fairly comfortable. It should be fairly easy for you to go through the rest of the motions to get to a final answer. That should be it for what we have covered today. I know we finished a little bit early. Hopefully all this stuff kind of made sense to you guys. Let me see if I can switch back to the verbal view. But yeah, so all the stuff covered that we did today was for the Heart of Algebra section. That's going to be that kind of core section that you'll see pretty consistently in the calculator section, but definitely heavily tested in the non-calculator section. These are, I think, good concepts to start off for in the early stages of studying, just because a lot of the additional types of work that you'll be doing are going to be building off of how comfortable you are with this section or subset of material. For example, if you're talking about Passport to Advanced Math, if you aren't comfortable with linear equations yet, it's going to be hard for you to be dealing with polynomials, quadratics, and that type of work, right? So most of you guys are going to have pretty good foundations in this area. If you want to just make sure you do, there are a lot of resources online for you to do that. There are a lot of resources that OneClass can offer you to do that. I would strongly suggest just spending time on doing that, on doing those practices. I'm a firm believer that lessons are really good for learning content, but in order for you to really master that for test day, that's up to you guys to do some homework, do some practice, and kind of just grind out those problems. Other than that, I really hope that this section today was helpful. We'll be doing additional sections throughout the week. I'll probably be talking about SAT math concepts that we haven't covered yet in additional lessons. And yeah, enjoy the rest of your weekend, and hope you guys have a good rest of the day.